Hello everyone, I am Dr. B.K. Singh and today I will discuss another oxidizing agent, that is the selenium dioxide. When you see this symbol, what comes to your mind? First thing, that it is what it is. Second, what it for. Third, what it can do. And honestly, these are very natural questions. And I must say, it should and it must come to your mind. And very simple answer to your first question, that is what is this? It is selenium dioxide, a well-known oxidizing agent. It is white or creamy white crystalline powder that turns slightly pink on decomposition. It has a pungent sour smell or odor, and it melts at 340 degrees centigrade, a high melting solid which can be easily synthesized by oxidizing selenium. And this oxidation can be achieved either by simply burning selenium in air or oxygen, or it can be synthesized by dehydrating selenious acid, and this selenious acid can be obtained simply by treating selenium with nitric acid, and this is the most convenient method for its preparation. Now come to see the structure. It is simply represented as a linear structure, oxygen double bond selenium double bond oxygen, but actually it exists as one dimensional polymer with alternate selenium and oxygen atom. It is an acidic oxide which is toxic in nature. It sublimes easily, and because of that its commercial sample can be easily purified by sublimation. So this is answer to your first question, that is what is this. Now come to your other questions that came to your mind, that what it for and what it can do. As you know that it is an oxidizing agent, and hence it can oxidize a variety of organic functional groups. Here I will discuss in brief that what it can oxidize. The first and the most important, it oxidizes allylic carbon and gives allylic oxidation, allylic carbon, allylic alcohol, allylic carbonyl. So allylic oxidation. Second, it can oxidize alpha position of the carbonyl compound. Alpha position of carbonyl compound to carbonyl 1 to carbonyl, and this is a well known name reaction, and it is called relay oxidation. It can also give benzylic oxidation. So benzyl group converted to carbonyl 1, benzylic oxidation. Not only that, it can give dehydrogenation reaction provided there is a beta hydrogen present in the molecule. So dehydrogenation reaction, that is removal of hydrogen. So removal of hydrogen and gives the alkene or olefin compound. It can also oxidize alcohols. So alcohol can be also oxidized with the help of selenium dioxide. So it will convert alcohol to carbonyl one. And nevertheless, it can oxidize alkynes and will convert into the dicarbonyl compound. So these are some representative examples of application of selenium dioxide, which we will discuss in detail one by one in due time. All right, before studying its application in detail, I will first try to make you understand its action, that is the mechanism how selenium dioxide work or act. As you know, or as you have seen, that it is known for allylic oxidation and oxidizes allylic carbon to alcohol or carbonyls. So I will try to make you understand its mechanism with one representative example. So kindly focus your attention and try to understand it. It starts with 4 plus 2 cycloaddition of selenium dioxide. Please pay attention. It starts with 4 plus 2 cycloaddition of selenium dioxide to give an allylic selenic acid. So, allylic selenic acid, cycloaddition to selenium dioxide. And it is analogous to Dalders reaction. If you recall, in this step, more nucleophilic end will attack on selenium, which is more electrophilic or electropositive in nature. Then oxygen will take up allylic hydrogen, this one, allylic hydrogen, and reaction will proceed. In the second step, this selenious acid, this selenious acid will undergo this 2,3 sigmatropic rearrangement. This is a different kind of reaction which we haven't seen so far. So this is a rearrangement of sigma bond, right? So we will not discuss about this right now. So it will go for the sigmatropic rearrangement and will give a very unstable compound. Further, this unstable compound decomposes to give allylic alcohol. So this will decompose to give allylic alcohol. And if the oxidation continues, then it will give the allylic carbonyl compound or alpha beta unsaturated carbonyl compound, and mechanism follow this route. So this is how selenium dioxide works. You must have realized that the reaction is very simple and straightforward. And I hope and believe that you must have understood this allylic oxidation nicely. Now come and try to understand other type of oxidation mechanism where selenium dioxide will oxidize alpha methylene group of the carbonyl compound. This type of oxidation is widely known as relay oxidation. In this oxidation, 1,2 carbonyl compound will form. Right. So, in this mechanism, you will see that it follows exactly the allylic oxidation pathways. And in this case also, in the very first step, more nucleophilic and attack on the electrophilic selenium and gives the selenous acid type of compound, which in the second step undergo the 2,3 sigma tropic rearrangement exactly in similar manner as that of allylic oxidation and gives a very unstable compound which on decomposition gives the 1,2 dicarbonyl compound. So this is how selenium dioxide oxidizes alpha methylene group to yield 1,2 dicarbonyl compound. Now I hope and believe that you must have a clear view to the mechanism of selenium dioxide. After good understanding of mechanism, now I will discuss some example. Now look at some allylic oxidation. In this example, that is in cyclohexene case, there is two allylic position. One, this. Two allylic position, but they are identical. So oxidation at either place will give the same product. So oxidation either take place here or take place here, the product will remain the same. There is no problem in this one. Now pay attention on the next example. This is a trisubstituted alkene. This is a trisubstituted alkene and it has three allylic carbons. So 1, 2, 3 allylic carbon. Theoretically, selenium dioxide can oxidize any of these three positions. However, preferentially selenium dioxide oxidizes only one position out of these three. So only one position and gives the corresponding carbonyl compound. This example highlights two important aspects of this reaction. First, that is the reduced selectivity, and second is the stereoselectivity. In such cases where these two important aspects, regio or stereo, play a role, and if alkenes are trisubstituted, then oxidation takes place selectively at more substituted end. So it will take place on the more substituted end and will give trans or E-allylic alcohol. For trisubstituted alkenes, there is reactivity order for allylic oxidation. That is, oxidation take place preferentially first at CS2 allylic position, then CS3 allylic position, then CH, if there is equal probability. Then the next question that must come to your mind, why at most substituted site or end of the double bond, and why trans or E isomer? To know these facts, we have to understand few things. So kindly pay attention on the next explanation. First, try to understand the reduced selectivity, and this reduced selectivity arises because nucleophilicity across both the end of the double bond are not symmetrical or same. You can see here nucleophilicity across the double bond is not same here or here. It is not same. And in this reaction, initially it involves preferential attack of the more nucleophilic end of the double bond at selenium. So this is the more nucleophilic end, and hence this will attack at the more electrophilic selenium. And because of this, it has a case transition state, and this simply justify the regioselectivity. Now come to the second aspect, that is the stereoselectivity, that is the trans or e-selectivity. It can be easily understood by looking at the cyclic transition state that forms during 2,3 sigmatropic rearrangement. You can see here in this cyclic transition state, that alkyl substituent adopts the pseudo-equatorial position. Once it acquires the equatorial position, it will, you can see here, it will give the trans isomer. And this is why it gives the trans or E isomer. So this is all about the regioselectivity and stereoselectivity. After clear understanding of the mechanism, including regioselectivity or stereoselectivity, now we can discuss some of its application. So I will start with allylic oxidation, or you may say oxidation of allylic compound. In this example, there is no issue of regio or stereoselectivity, so oxidation may take place at either allylic position, but it will give the same product. So this is allylic position, this is also allylic position, but both are same, so it will give the same product. In this example, it is trisubstituted one. So it is trisubstituted alkene, so it will follow what we have understood so far and what we have discussed so far. Oxidation will take place at most substituted end of the double bond. So this is the most substituted end of the double bond. This is allylic position, this is allylic position. And then will follow the reactivity of allylic carbon, CH2, CH3, CH, and then trans or E isomer. So this will be the predominant or major product. Once again, in this example, it is trisubstituted alkene and will follow as previous example, that is more substituted end of the double bond, then will follow the CH2, CH3 reactivity order, and then trans or E isomer. So this would be the major product, right? But this is the very interesting example. There are two separate double bond, and both the double bonds are trisubstituted. If you see this one, 1, 2, 3, 1, 2, 3. So both the double bonds are trisubstituted, but it is giving exclusive one product. You see here, it is giving exclusive one product. So I request all of you to try it and explain the observation by yourself. For assistance, as usual, you may drop your comment or message and we will discuss it. But honestly speaking, try to do by yourself. This is very good example to give you the confidence about entire selenium dioxide. Once again, this is a trisubstituted alkene and giving expected product, more substituted side trans and so on, and this is aldehyde because over oxidation is taking place. So more substituted side and trans is the major, so this is the major product. In this example, there is only one allylic position. So this allylic position is converted to allylic alcohol and giving the product exclusive at this position. So there is no confusion about regarding the allylic oxidation in this case. So these are few representative example of allylic oxidation. Now we will focus our attention on the benzylic oxidation. Let us discuss some example of benzylic oxidation. In this, we will see the conversion of benzyl group into CO, carbonyl. The first thing, what is required for such oxidation? Simple. Active methylene CS2 group. It will convert CS2 to carbonyl CO. For example, in this, methyl group is active, which oxidizes to, this methyl group oxidizes to CH2 by selenium dioxide. If you see carefully, this CH3, CH2H is converted to C double bond O and this hydrogen here. So this is CHO. Right. Similarly, in this case also, this methyl group is getting converted to the carbonyl one. In the next one, benzylic position, this benzyl position is getting converted to the carbonyl one, CS2. So CS2 is getting converted to CO. In another one, here also it is this CS2 is getting converted to CO. No problem. Now, after this example, let us try to understand the mechanism of this transformation. It is simply the analogous of allylic oxidation. More nucleophilic end of the double bond will attack on the selenium, which is electrophilic, and then oxygen will take up this allylic hydrogen and will give the this selenous acid kind of compound, which undergo the 2,3 sigma tropic rearrangement and give an unstable compound, which on hydrolysis give the carbonyl compound. So mechanism of this benzylic oxidation is also very simple. There is no complication because we have seen the allylic oxidation, how it take place, then alpha methylene oxidation, how it take place, and it is also following the same. So mechanism now appears very simple to us, and it is indeed a very simple. So it can oxidize. This is the third example. So first it can oxidize allylic position, then alpha position of the carbon compound, and the third one is the benzylic oxidation. Now come to the next one, that is the oxidation of carbonyl compound. Sorry. Let us discuss the oxidation of carbonyl compound. Please keep one thing in the mind, that this oxidation is effective. That means oxidation of carbonyl compound is effective when there is no beta hydrogen present in the molecule. If there is beta hydrogen present in the molecule, then dehydrogenated product will also form. For example, in this case, alpha hydrogen, alpha position, CH2, this CH2 is getting converted to, CO and this H. So, alpha position is oxidized to CO with the help of selenium dioxide, and this is the oxidation of methylene carbon. Similarly, in this example also, methylene group is getting converted to the carbonyl one. So Ca2 to CH2 to CO. In this example also, this alpha methylene group is getting converted to carbonyl. In all these cases, here also this is alpha methylene group which is very easily converted to the carbonyl in presence of selenium dioxide. Here too, this is getting converted to carbonyl, and these examples also you can see it has a active methylene group, it has an active methylene group which is converted to carbonyl compound. So these are few representative example of oxidation. Regarding its mechanism, we have seen its mechanism in detail earlier, so no need to discuss it here, right? Now we will discuss another type of reaction, that is the dehydrogenation reaction of selenium dioxide. For such reaction, that is dehydrogenation reaction with selenium dioxide, the essential condition is the presence of beta hydrogen. Dehydrogenation will only take place where there is active alpha methylene group and beta hydrogen present. And keep this thing in mind that this reaction will take place when it is performed at high temperature. So this compound, it has alpha methylene hydrogen and beta hydrogen also present in this molecule, and hence it gives dehydrogenated product, that is converting this into the olefin or alkene, corresponding alkene. Similarly, in this also alpha hydrogen and beta hydrogen is there, and it is getting converted to the corresponding alkene. So selenium dioxide can also give the dehydrogenated product. Now try to look at its mechanism, how it is taking place. There are several proposed mechanisms for this dehydrogenation reaction. I will discuss only two which are in fact widely accepted. In the first step, enol form of the keto compound or carbonyl compound react with selenium dioxide. So this is enol form of the carbonyl compound that will react with the selenium dioxide. As per Spire, beta hydrogen transfer will take place and will give the dehydrogenated product, that is the corresponding alkene. And if we consider the another one, that is a Sharpless one, so in this case also enol form, this is the enol form of the carbonyl compound, will react with selenium dioxide to give selenous acid kind of compound in the very first step, and then syn elimination, this syn elimination will give the dehydrogenated product, that is the corresponding alkene. So from both the mechanism, it is clear that the presence of beta hydrogen is a must. Without it, selenium dioxide cannot give dehydrogenated product. So, if we want to get a dehydrogenated product from some carbonyl compound or some organic compound with the help of selenium dioxide, so two essential things which we have to keep in our mind. One is high temperature, really high temperature, and second, that active methylene group must be preceded by the beta hydrogen. If these two conditions are met, selenium dioxide will give the dehydrogenation reaction and product. Now, at the end, we will discuss the oxidation of alkyne with selenium dioxide. So, selenium dioxide can very easily oxidizes alkyne into dicarbonyl compound, provided there is sulfuric acid present. There is sulfuric acid present in the reaction. In absence of sulfuric acid, it cannot oxidize alkynes. So, in a reaction, if there is sulfuric acid present, then selenium dioxide can oxidize internal alkynes or terminal alkyne into dicarbonyl compound, this dicarbonyl compound. So, this selenium dioxide can give a variety of reaction. If we want to summarize it, it can oxidize allylic one, it can oxidize carbonyl compound, it can oxidize benzylic group, it can oxidize alcohols, it can oxidize alkyne, it can also give the dehydrogenation reaction. So variety of oxidation can be achieved by this selenium dioxide. So this is all about the selenium dioxide, which I have tried to cover in detail. But if still you feel like there is some problem, you may write your comment and I will explain. But I really and seriously suspect that there would be any confusion to you, because we have seen all the aspect in really detail, all different kind of reaction with its mechanistic detail. So there should not be any confusion. However, if there is, don't hesitate to write a comment to me, and certainly I will explain whenever it would be asked to me. Thank you and good luck to you.